Camp, we're now going to do problem 12. Problem 12 is going to be a continuation of problem 10. And then we had a particle that came in and collided perfectly inelastically with another particle. This time it says a particle of mass 2 times 10 to the minus 15 kilogram is coming in at, this is the same speed that it was in problem number 10, 0.95, the speed of light. And it comes crashing into a particle of mass 5 times 10 to the minus 14 kilograms. So that would be what? 50 times 10 to the minus 15 kilogram, if you make it the same power, right? And then this one is originally at rest. In that problem, in problem 10, we had the collision be perfectly inelastic. In this case, it says assume the collision is perfectly elastic. So based on things that we learned in problem 11, which was in between the two, in problem 11 we did a particle undergoing decay, and we wanted to find out the velocities and the kinetic energies of the particles undergoing this decay. So based on that problem 11, we're going to solve the elastic collision version of what we did in problem number 10. Okay? So let's see here. Well, we originally calculated the gamma of the particle in that problem. Remember, gamma is square root of 1 minus 0.95 squared. And when we solved that, gamma came out to be 3.20. Okay, so basically what's happening here is momentum initial. We have to send it to equal to momentum final total. Initially, the momentum is the gamma initial of the incoming particle times the mass, rest mass of the incoming particle times the velocity. And then that one is going to equal, well, after the collision, basically, you're going to have, let's draw this. You have 2 times 10 to the minus 15. It's going to be certain velocity v1, and 50 times 10 to the minus 15, certain velocity v2, right? So we're going to need the gamma of that particle, right? We can call that gamma 1, and then m0 v1, and then we're going to need the momentum of this one, gamma 2 m0 2 times v2, right? So let's put down what we have so far. The mass of the incoming particle, 2 times 10 to the minus 15. The velocity of the incoming particle, 0.95, the speed of light. So I'll keep it as that. I won't put down what the speed of light is. So our answer will be in terms of the speed of light. And then we have here gamma 1, which we don't know. And then we have here m0, which is 2 times 10 to the minus 15. And then we have v1, which we don't know, plus, and then we have gamma 2, and then this one is 50 times 10 to the minus 15, and then v2, right? What do we have so far? Well, the 10 to the minus 15, 10 to the minus 15, 10 to the minus 15 cancels out. And I could also divide everything out by 2. Divide this by 2, divide this by 2, divide this by 2, and simply just have 3.20 times 0.95. So this will be 3.04 times the speed of light, c. And then the 2 will cancel here, so we'll have gamma 1 v1. And then the 2 into 50 goes in 25, gamma 2 v2. Now remember, in problem 11, we derived the relationship between v1 and gamma, and we said we might be able to use this once in a while. Whenever we have two expressions, we don't want to have both of them. And the expression was v was square root of gamma squared minus 1 over gamma. Right? So this is a good opportunity to substitute that. So we basically will have 3.04c. If you multiply gamma times v, what do you get? Gamma times v, we have square root of gamma squared minus 1. So you only have one unknown variable. So this one will be square root of gamma 1 squared minus 1 plus 25 square root of gamma 2 squared minus 1. Okay, so now we have one equation, right? Now we need another equation, and that equation is going to come from the kinetic energy conservation. Okay? Kinetic energy initial must equal to kinetic energy 1 plus kinetic energy 2. What's the initial incoming kinetic energy? Gamma initial minus 1 m0 c squared is equal to gamma 1 minus 1 m0 1 c squared plus gamma 2 minus 1 m0 2 c squared. Okay, this is again 3.20 minus 1. This is 2 times 10 to the minus 15. I'm not going to put the power 10 to the minus 15 because they're going to cancel from both sides. C squared is also going to cancel. So I'm not going to need that, c squared, c squared. So you're just going to have just the 2, right? So this one you have gamma 1 minus 1, 2, plus, then you're going to have here 50, gamma 2 minus 1. Okay? So what do we have? Well, 3.20 minus 1, that's going to be what? 2.20 times, well, actually it's probably better just to even divide by 2. Divide by 2, divide by 2, divide by 2, and you just simply have 2.20 is equal to gamma 1 minus 1, right? Plus 25 gamma 2 minus 1. The 2 goes into 50 25 times. Here is your second equation. Well, the best way to solve this is basically substitution. To say, take everything to the other side, and then you have 2.20, and then the minus 1 goes over there, becomes plus 1. And then 25 distributes into there, becomes minus 25, right? When it goes to the other side, it becomes plus 25. That's equal to gamma 1 plus 25 gamma 2. So 26 plus 2.20 is going to be 28.2, right? 28.2, so let's write that in. 28.2. That's equal to gamma 1 plus 25 gamma 2. Well, here's what I'm going to do. I'm going to say gamma 1 from this. Gamma 1 is equal to 28.2 minus 25 gamma 2. So substitution basically, and then substitute that into here, right? So 28.2 minus 25 gamma 2 is an expression for gamma 1. Substitute that there. 3.04 C is equal to square root of 28.2 minus 25 gamma 2 squared minus 1 plus 25 square root of gamma 2 squared minus 1. Okay? The rest of this again is good time to use the solver. Okay? Well, actually, as a matter of fact, this one I am actually missing a c, the speed of light c, because this is unitless. This is unitless, so this is just a number, and you need a unit. So this is in terms of c. So gamma v is equal to square root of gamma squared minus 1 times c. So I was missing the c. Well, if you put that c here, what's going to happen? The c will cancel, and you just basically have 3.04. Okay? So this kind of calculations for elastic collisions is best done in this sort of format. Get the momentum equation, substitute v in terms of c, put it into here, have an expression just with gamma. Then take your kinetic energy, substitute for gamma, put it into the momentum equation, and then you have just the unitless equation here. The answer we're going to get for gamma is going to be some unitless number. Okay? So let's put it into the solver. The answer comes out false. In that previous problem, we also had a similar situation where there was no answer. And from there, we figured out what that meant. It meant, in that case, it was a particle coming in problem 10. there was a particle coming and it was dividing up, decaying into two particles, and we had set up our equation so that one of them goes forward, the other one goes backward, and it ended up that there was no solution. So it meant that both of them go forward. It was the neutron and the pion, both of them go forward. In reality, what's most likely going to happen is that the neutron will go up at a certain angle and the pion will go up at a certain angle in that case. So the original sigma particle will come forward, decay, both of them go forward and go off at different angles. In this case, how did we set it up? Well, we assumed the 2 kilogram came and hit with the 50, and they both are going forward, but this probably means the opposite is true. The 2 should be going backward, right? That kind of makes sense if you think about it, because the 50 is much heavier. So if the 2 times 10 to the minus 15 kilogram is coming, hits a 50, it's most likely going to bounce backward. So how should we fix this? Well, the kinetic energy equation stays the same. The only one that changes is that over here, we put negative. Okay? Why? Because the momentum of the 2 times 10 to the minus 15 kilogram is going to be back. This one will be positive. So this one therefore should be negative. This one therefore should be negative. And this one should be negative. Okay? So all I have to do now is go back to my calculator and change the sign of this into a minus. Okay? So go back. Comes out to be 1.0235. And therefore, what is that? Gamma 2 is the gamma of the 50 times 10 to the minus 15 going forward, right? So therefore, what's going to be gamma 1? Gamma 1 is going to be 28.2 minus 25 gamma 2. So let's do 2.612168, right? Gamma. So gamma 1 is the particle that went back, okay? So now we can translate that to velocities. The heavier particle, we can call that the V50. That's going to be square root of 1.0235 squared minus 1 over 1.0235 times speed of light. So 0.95, the speed of light comes, hits a 50. It's a mass that's 25 times greater, right? That goes forward at 0.2% the speed of light. Basically, 21% of the speed of light, right? 0.213 times the speed of light. And then the V of the 2, square root of gamma, square root of minus 1 over gamma times C. And then you're going to put the 2.6121168 squared minus 1 over 2.612168 times speed of light for the speed of light. Okay? So the 0.95, the speed of light comes, the 2 times 10 to the minus 15 hits a 50 times 10 to the minus 15, it bounces back quite fast. 0.924, the speed of light, the heavier one goes forward at 0.213, the speed of light, and this conserves their kinetic energy and their momentum. So now you know how to apply different types of problems to relativistic dynamics, inelastic and elastic collisions. Okay? Thank you very much.